Paris is the capital of what? Try filling that gap without looking back at the first word. You cannot do it because the answer depends entirely on where you started. Now imagine a computer trying to read that sentence. The old way worked exactly like reading through a tiny window. You could only see one word at a time, process it, and then slide over to the next one. Let us map this out on our architecture. We can draw the old pipeline as a chain of small boxes, each holding just one word. Watch what happens to the memory signal as it travels down the line. By the time it reaches the final word, the information from Paris has faded into nothing. The model guesses wrong because it literally forgot what it was talking about. You have probably seen this limitation in real life. Early chatbots would constantly lose the thread after just 2 lines of conversation. They were not broken, they were just still reading through that tiny window. So what if we took that window away completely? What if the model could look at every single word in the sentence at the exact same time? That one shift is the reason ChatGPT class models exist at all. But seeing every word at once creates a brand new problem. How does the model decide which words actually matter to each other? Next, in the one idea behind transformers, we will see how reading the entire sentence at once lets each word decide which other words matter to it. Last time we saw why computers struggle with language when they process it, one rigid step at a time. But you do not read like that. When you read a sentence, your eyes jump back and forth. You look ahead for structure, then glance back to anchor meaning. It feels instant, but your brain is constantly cross-referencing every word against the rest of the paragraph. Here is our pipeline layout so far. We drop that sequential chain entirely. Instead, we park a single white transformer box at the end of the lane. All 5 words enter together as parallel arrows. Inside, we draw a light web connecting every word to every other word. We give that cross-referencing a name. It is called attention. Each word pays attention to the others, deciding which ones matter most for its own meaning. The weights shift depending on context, so the same word can mean something completely different just by looking at its neighbors. This changes everything about speed. The old chain had to finish word 1 before it could start word 2, so a long sentence just crawled along. If you have ever stared at a loading bar while waiting for a model to process text, this is why that old way felt so heavy. A transformer has no such bottleneck. Every word is worked on at the exact same time. And that parallel shape matches exactly what a modern GPU was built to do. We start with old training pipelines. Then we add a parallel GPU. That GPU processes massive internet-scale text. And out comes a much better model. So the data flows from that slow pipeline into the GPU, jumps to the massive text, and lands on a superior model. Here is the full map we are walking through. We have raw text on the left. Next comes a number converter. Then sits the transformer box. Finally, a predicted word exits right. So the signal travels from raw text into the converter, flows through the transformer box, and arrives at the predicted word. Every model you will call in your career, from GPT to Claude to Llama, runs this exact transformer box underneath. The raw text enters left, the numbers flow through, and the prediction exits right. Once you see how attention works, the rest is just scaling it up. Next, let us look at tokenization, which chops raw text into numbers. Now that we know how transformers weigh every token against every other token, let us look at where those tokens actually come from. We add a new component right after our input and we call it the tokenizer. It takes our raw sentence and prepares it for the model. Watch how the sentence splits into separate chips, starting with Paris. Notice how the space travels with is. Then comes the space and the word the, followed by capital and off. Watch a long word like extraordinary. It does not stay whole. The tokenizer breaks it into extra. then OR, then D, and finally NAD. This works because the model relies on a fixed dictionary of chunks, usually holding tens of thousands of entries. That single list can spell out any word in any language, even ones it has never seen before during training. Each chip then gets a plain ID number sitting right underneath it, which is just the row number where that chunk lives inside the dictionary. The model never reads text at all, it only processes these numeric IDs. Keep in mind that a token is not always a neat word piece. Some tokenizers will split straight down to a single character if they need to. So the honest statement is simply that the model works in token IDs rather than claiming it can never see a letter. Because every provider builds its own dictionary, different models will chop the exact same sentence into different counts and shapes. That is why your prompt might be 100 tokens on one platform and 85 on another. This matters because the token is the exact unit your API bills you in. It is also why the model will sometimes miscount letters inside a long word. Next, let us see how those IDs become your actual costs in tokens or money reading your API bill. Now that we know how the tokenizer chops text into pieces, let us look at what those pieces actually cost. Picture a short paragraph on a page. The tokenizer cuts it into strips, and each strip is just a few characters long. So a whole paragraph usually breaks down to a few hundred strips. You can guess roughly, but the only reliable count comes from running your text through the real tokenizer. Let us pin this pricing model to our pipeline layout. We add a token counter strip along the top and a price panel right next to it. Say we send in a prompt that counts 120 tokens. The transformer processes them and streams back a reply of 80 tokens. Both numbers sit on that counter, ready to be multiplied by your provider rate. Here is where most people trip up on their first bill. You do not just pay for what you send in. You pay for the input tokens and the output tokens separately, and providers usually charge different rates for each. Reading costs less than writing, so your reply often runs pricier per token. Watch out for the agent trap. If your code loops 10 times to refine an answer, it does not just send a few new words each round. It resends the entire growing conversation history every single time. By the 10th loop, you are paying for a small novel just to repeat what was already said. The cloud provider loves it, your wallet does not. The fix is a simple habit you can start today. Measure your token counts while you are building, not after the monthly invoice lands. Keep that counter visible in your local tests so you see exactly how your prompts scale before they hit production. That is why every AI engineer watches this number. Token count is the single dial that controls both your cloud bill and your response speed. Keep it lean, keep it predictable, and next we will see how a token ID, which is just a row number, becomes a list of numbers that actually carries meaning. We start with raw text, which the tokenizer chops into tokens. If Paris becomes token ID 4821, that number is just a row index in a giant dictionary. There is zero meaning in 4821 itself. You cannot do math on row numbers and expect the model to understand geography or grammar. Imagine you want a computer to compare two people. You could just use their names, but names are arbitrary labels. Instead, you describe them with a set of scores: height, age, friendliness, and energy level. Now you have numbers that actually mean something. If Alice scores high on friendliness and Bob scores low, the math immediately tells you how they differ. The transformer does exactly this with words. It takes each token ID and passes it into a giant table. That lookup links the raw index to the table. But instead of returning a single number, it hands back a long list of learned scores. This output connects the table to a new vector format. Look at what happens when we run a few words through this table. The embedding for Paris lights up in certain positions, and the embedding for capital lights up in almost the exact same places. They share a pattern because they relate to cities and capitals. Meanwhile, the tiny filler word is gets a completely different pattern. The numbers themselves are now carrying meaning. Here is the best part. Nobody sat down and hand-wrote these scores. We start with raw text, which enters a training loop. That loop produces the final embedding weights. As it runs, the system reads billions of sentences and adjusts those numbers until related words keep similar patterns. We just saw how a row number becomes a list of scores. Now let us plug that embedding layer into our pipeline. Right after the tokenizer chops up the text, we now have the embedding layer. Each token chip travels here and turns into one of those meaning-packed number columns. This is exactly the same mathematical object you will store in a vector database when you build retrieval augmented generation later in this course. The model does not read words anymore, it reads geometry. Next, we will see why reading all these columns at once leaves the model completely blind to word order, and how we fix that by adding position directly into the numbers. Now that we have turned our tokens into meaningful numbers, let us see what happens when the model reads them all at once. Compare dog bites man with man bites dog. They share the exact same words, but their meanings are completely opposite. Because attention looks at every token simultaneously, it sees only a bag of words and ignores where each one sits. We just mapped every word to a vector, but those vectors have no idea where they sit. Let us look at that gap on our diagram. We tokenize the input, count the tokens for pricing, and pass them through the embedding layer into the transformer. But notice how those embedding columns slide straight in without any record of their original order. So we fix it in one line. We add a position box that stamps each token column with a symbol marker that says which slot it occupies. These markers merge with the embedding columns, carrying the order all the way down into the transformer. Think of it like seat numbers on a train ticket. You can have the exact same passengers traveling together, but the seat number tells you who sits where. Swap the numbers and the whole arrangement changes. We call this positional encoding. It is the quiet repair that gives order to a parallel read. And it is exactly why the order of instructions inside your prompt genuinely changes the answer you get back. Next, let us look at the transformer block and see how it actually uses these ordered columns to weigh every word against every other word. Let us pull back and trace our full pipeline layout, starting from that positional encoding we just mapped. That big transformer box is not some giant tangled mess of wires. It is built around one single unit doing all the heavy lifting. Think of that unit as a factory station on an assembly line. Raw material rolls in on one side, gets processed, and an improved product rolls out on the other. In our model, that raw material is a column of numbers representing each token. The station takes those columns in and hands back better columns out. Notice what stays exactly the same. 5 tokens go in, 5 tokens come out. The shape never changes. If we peek inside that processing zone, you will find exactly 2 parts working together. We are going to open the first one in the next few videos. Here is where things get interesting. One single trip through this station is not enough for the model to truly understand a sentence. Video 13 shows exactly what the architecture does to fix that. That is why every AI engineer stares at this one box. Everything people mean when they ask what happens inside a large language model actually lives right here. Next, let us step inside that first part and see how each token looks across the whole sentence and pulls in meaning from the words that are relevant to it. Now that we have opened the transformer block, let us look at what actually happens inside when the model reads a sentence. Consider this simple line. The trophy did not fit in the suitcase because it was too big. Pause for a second. What does the word "it" refer to here? Your brain instantly knows it means the trophy, not the suitcase. And that is exactly what self-attention does. It draws a strong connection from the pronoun back to the noun that makes sense. Put simply, self-attention is a mechanism where every single token looks at every other token and asks one question. How much do you matter to me right now? And here is the crucial detail. Those connections are never all the same size. Some arrows grow thick because the words are closely related, while most stay thin because they carry little shared meaning for this specific token. You might wonder why we call it self-attention. It is because the sequence is only looking at itself. It does not reach out to an external database or a reference document. All the context it needs is already sitting right there in the input. This is why you should care as an AI engineer. Every time your agent resolves a pronoun like it, or tracks down that file, or recalls the previous step in a long prompt, self-attention is doing the heavy lifting. We have built quite a pipeline together, so let us see exactly where this fits. Right inside the transformer block, we place the self-attention module. That is where each word reaches out to every other word in our running sentence, pulling heavily from Paris and lightly from the rest. So self-attention is simply words looking at other words, weighing their relevance, and combining them into a richer picture. But how does the model actually calculate those weights without guessing? Next, let us look at query, key, value, the library analogy. We just saw how every token looks at every other token inside self-attention, but we left the actual matching process a little vague. So let us step away from the math for a moment and picture a quiet library instead. You walk in holding a short slip of paper, ready to scan the shelves without accidentally checking out the entire encyclopedia. Think of that question as your query. It is just a short note you write down, saying exactly what you are looking for. In our model, every single token gets its own little query note like this. Now look at the shelves. Every book has a label on its edge telling you what it is about. That label is the key. It does not hold the whole story, it only advertises what is inside. And if that label catches your eye, you open the cover and read the pages. Those pages are the value. This is the actual information you take away once you have made your choice. Let us say the token holding the word of sends out its query, asking for location details. It scans the keys on every book, and the one reading Paris matches best. So the pages inside that Paris book flow right back into off, giving it exactly the context it needed. See, the library is just a picture to help it land. Inside the real model, these are actually 3 learned mathematical transformations applied to every token vector. And that is enough to build on for this whole course. Let us pin those rules onto our pipeline layout so you can see where they live. Each token inside self-attention carries a Q tag, a K tag, and a V tag, just like the legend shows. Why does this matter to you as an AI engineer? Because the exact same query key value idea shows up whenever you build retrieval over a vector store. You can see the Q tag handles the search, the K tag handles the match, and the V tag holds the payload. Next, let us look at how those matches become actual percentages and why every token's attention always adds up to exactly 100%. Now that we have hung Q, K, and V tags on every token, let us see how they actually talk to each other. Think of attention as a strict budget. Every single token gets exactly 100 points of focus to spend across the whole sentence. No more, no less. Let us trace where those query and key tags actually meet inside our pipeline. We will watch that split happen right under the self-attention module. See, every match score comes from one simple comparison. The query tag on a token reaches out and checks against the key tag of every other token in the sentence. Those raw matches are just rough strengths telling us which words look similar so far. But raw strengths are messy, so we run them through a step called softmax, which simply turns those scores into clean percentages that add up to exactly 100. The numbers on screen are just illustrative to show the shape. Watch how the budget splits for the word of. This is where the budget rule bites you. Focus is completely zero-sum here. If Paris grabs a bigger share, Another word must lose that exact amount to keep the total at 100. You cannot give everything to everyone. And this split is never the same twice. If we look at the word capital instead, it does not care about Paris nearly as much. It pours its focus into of and the because those words define what kind of city it is talking about. The budget reshuffles entirely for every single token. Now count the actual work happening here. With 5 tokens, every single one compares against all 5, giving us 25 comparisons right there. Double the tokens to 10 and it becomes 100 comparisons, not 50. In simple words, the work grows at a rate of big O of n squared. This is why you should care as an AI engineer. Because focus is zero-sum, stuffing 50 instructions into one prompt means each instruction gets a thinner slice of attention. And because the comparisons grow quadratically, the compute cost of a long prompt grows much faster than its length. Next, let us look at how the model runs attention many times in parallel instead of once, because different heads notice different kinds of relationships. In our last video, we split 100% of a token's focus across the words around it. But what if that single split is too narrow? Let us say you hand a paragraph to 3 people for proofreading. You have a grammar teacher checking your commas, a fact checker verifying your dates, and a tone editor reading for your voice. Each person highlights completely different parts of the text because they are looking for something different. And you want all 3 opinions before you sign off, mostly because you do not want to be the one explaining the typo to your boss on Friday. That is exactly what multi-head attention does inside the transformer. Instead of running one single set of queries and keys, the model runs several attention calculations in parallel. Let us call them heads. Each head learns its own separate projection matrices, so it can focus on a different kind of relationship in the exact same sentence. See, our pipeline layout so far holds everything we have built. Look at how they disagree on purpose inside self-attention now. Take our token off from earlier. Head 1 might dump 90% of its attention onto the word before it, tracking grammar. Head 2 could spread its focus evenly across the whole sentence, mapping who did what. And head 3 might lock entirely onto a single name, tracking the topic. Each head gets its own percentage bar, and they do not compromise. Now comes the clever part. These 3 independent readers never talk to each other while they work. But once they finish scoring, their results are stitched back together into one single vector per token. The model takes all those different perspectives and merges them before leaving the self-attention module entirely. We only drew 3 heads here to keep it readable, but real modelers run far more. The merge point simply scales up to handle dozens of parallel streams instead of 3. You will always find the exact count published on the model card because it is one of the first knobs engineers tune for performance. This is why one single model can track grammar, facts, and your instructions all at the same time. Without multiple heads, you would be forcing every relationship through one narrow lens, and complex prompts would simply fall apart. Next, let us look at the feed-forward layer, where after tokens gather context, each one is processed on its own against everything the model learned in training. Now that we have seen how multi-head attention lets every token look at every other token, let us split the transformer block job in 2. Think of it like a team meeting. Attention is the meeting itself, where everyone shares updates and gathers context. But once the meeting ends, each person walks back to their own desk to process that information privately. That quiet work is exactly what the feed-forward layer does. Now let us trace where that private processing happens in our architecture. Right after the self-attention module sits the feed-forward network. Notice the visual difference here. There are no crossing arrows at all. Each token enters its own separate lane and is handled completely independently of the others. So what actually happens inside those separate lanes? This layer holds the model baked-in training knowledge. It is nothing but a massive collection of learned facts and patterns stored as mathematical weights. For example, if the token Paris arrives here, the feed-forward network quietly checks its internal patterns and boosts the probability that this word belongs to a country. And honestly, this is where the real scale lives. A large share of a model total parameters sit in these feed-forward layers rather than in attention. We are talking about millions upon millions of tiny weights working together, which is why these blocks take up so much memory on your GPU. This matters to you as an AI engineer because the feed-forward network is the actual vault for what the model learned during training. It does not look up live facts on the internet. It only ever uses what was baked in, which is exactly why a model can be so confidently out of date when you ask it about recent events. So attention gathers context, and feed-forward applies knowledge. But one block is rarely enough to understand a full sentence. Next, let us look at how stacking these layers builds meaning from spelling all the way to deep understanding. Now that we have seen how the feed-forward layer processes each token privately, let us stack those blocks together. Suppose you're reading a thick legal contract for the first time. You just catch names and dates on the first pass. By the third read, you see who owes what to whom. And by the 10th read, you understand the whole intent of the agreement. Nothing is assigned to a particular read, you simply carry more understanding each time. Let us trace where this gradual build-up happens inside our pipeline. We just put one transformer block in there, but a real model stacks many of these identical blocks, one after another. Each pass leaves each token holding a slightly richer version of itself. The understanding is spread across all the blocks rather than divided between them. See, this is the bit that looks wrong and is not. You will see tutorials online claiming the first block handles spelling and the second handles grammar. But researchers can only observe that later blocks carry more context than earlier ones. The stack just continues, repeat many times down the line. No single block is ever truly the grammar block. In simple words, the blocks are identical in shape from top to bottom. They all hold the exact same self-attention and feed-forward parts. The trick is that each one has its own learned settings, tuned during training to pick up slightly different patterns. So basically, this stack count is what separates a small model from a large one in the real world. A model with just 12 layers will be quick and cheap to run. But if you add 60 or more layers, it becomes much smarter at complex reasoning, while also growing slower and more expensive per call. This is exactly why an AI engineer picks a small, fast model for simple routing tasks and reserves the large, heavy one for hard reasoning problems. Next, let us look at what the model actually produces at the end. Not a sentence, but just a ranked list of candidate next tokens. We just saw how each block refines the context step by step. Let us trace where that final signal lands. At the very end, we attach an output stage that produces this ranking. And here is the punchline of the whole series. An LLM is nothing more than a next token guesser. Suppose our input stops at Paris is the capital of. The model looks at its entire token dictionary and assigns a likelihood to every single option. France leads at 82%, then the word the gets 6%, Europe follows with 4%, and Italy trails at 1%. I want to be clear that these exact numbers are just illustrative, but the shape is always the same. See, there is no hidden answer object sitting in memory, and the model does not look up facts from a database. We call this a probability ranking over its token dictionary. The highest score simply means that option fits the pattern best. Think of it like a reader finishing a puzzle after studying millions of books. You are not pulling out random letters. The system matches deep grammatical and factual patterns before it predicts the next word. Guessing well at this scale is what makes it feel intelligent. But here is the catch. The model does not know whether its top pick is actually correct. It only knows what is statistically likely given the context. Probability is not the same as truth. is exactly why an AI engineer cares. Because the model always outputs a ranked list, it will never simply say, I do not know. It will always hand you the most likely guess, even when it is completely unsure. You have to explicitly prompt it to admit uncertainty. So, we have our ranked list of candidates ready to go. But how do we actually pick one from that list? Next, let us look at temperature and how boldly the model picks. Now that we have our ranked list of tokens, let us see how one actually gets picked. The model hands you a ranking, not an answer, so something still has to choose. That is where temperature comes in. It is the single setting that decides how strictly that ranking is obeyed. Drag the slider near 0, and the list sharpens dramatically. The top token almost always wins, and if you run the same prompt twice, you get the exact same answer. It plays it safe. Push the slider higher, and the list flattens out. Unlikely tokens get a real chance, which makes answers creative and completely unrepeatable. Almost everyone lands this one wrong at first. Temperature adds no new knowledge and fixes no errors. It only changes how boldly the model picks from what it already has. So for your course project, keep it near 0 for extraction, tool calls, and JSON output. Bump it higher only when you want brainstorming or copy. If you are building an agent that must call tools reliably, run it at a low temperature. You do not want it guessing the wrong function name. The output list gives us probabilities, but nothing has actually picked a winner yet. Let us trace where that final selection happens in our architecture. We add a sampling stage right after the output box, which carries a controls panel. On it sits our temperature slider and a pointer to the winning token. We leave empty space on that panel for another control, because we will add one shortly. And once temperature has reshaped those chances, there is another control that trims the unlikely tail before anything is chosen. Next, let us look at top P, trimming the list before the pick. Now that temperature has reshaped the probabilities, we still face a crowded shortlist. Temperature changed the shape of the list, but this new setting changes which entries are even allowed in the running. See, top P works by keeping only the smallest group of top tokens that together cover most of the probability. It throws the long tail away entirely. Watch what happens when we slide the cut line down. More candidates survive the filter. Now push it up, and only France and Italy make the cut. The rest get politely shown the door. Let us trace back through the sampling stage we mapped earlier. This is its own separate value in your API call, and changing it does not change temperature. Put the two side by side in one line, temperature decides how boldly to pick, top P decides what is on the table to pick from. Why an AI engineer cares? Top P is the setting you reach for when a low temperature still lets nonsense slip through. Next, let us look at how a single next token guess turns into a full paragraph because the model reads its own output back and runs again. Now that top P has trimmed our candidate list, let us trace how that single guess becomes a full answer inside our pipeline. But it only ever gives us one word at a time. Let us say we feed in Paris is the capital of. The pipeline runs, sampling lands on France, and we get our first answer token. But the loop does not stop there. That winning token gets fed right back into the tokenizer. So now the model reads Paris is the capital of France and runs again to guess what comes next. See, this means the entire paragraph is reprocessed on every single step. The model does not just look at the last word, it reads everything from the start again. It is like rereading your entire email thread every time you want to hit reply. Watch the token counter climb with each pass. 5 tokens for the prompt, 6 when France joins, then 7 as the next one arrives. And here is the bill for it. Look at the price panel climbing as the counter rises. Every extra token gets billed on top of what you have already sent. So longer answers take more time and cost more with each step. It is like paying for the whole menu every time you order one extra side dish. This is exactly why your chat windows stream the response word by word instead of handing it all at once. The model has to finish each step before it can start the next one, so you watch the sentence build up live as the loop spins. You get to watch it think, which is great for suspense and terrible for patience. So how does it ever know to stop? The loop keeps spinning until one of two things happens. Either the model predicts a special end token that signals the thought is complete, or it simply hits your max tokens limit and cuts itself off. The thing is, this reprocessing sounds expensive, and it is. That is why modern models cache their earlier calculations, so each new token becomes much cheaper to compute without you having to change a single line of code. This is why you should care as an AI engineer. Output length drives latency almost linearly. If you build an agent that thinks out loud, asking for brief reasoning genuinely makes the system faster. Next, let us look at the context window and what happens when a conversation grows past that fixed limit. Now that we have seen how the generation loop picks one token at a time, let us map where this boundary sits inside our pipeline. This is the context window. It is nothing but the maximum number of tokens the model can look at in a single request, your prompt plus its reply together. And here is the thing that catches people out. This size is not some fixed universal number you can memorize. It is a property of the exact model you are calling, and it changes with every new release. The numbers have grown a great deal since those first chat models, but they still differ wildly from one provider to another. So always check the documentation for the model you actually run. So why does this limit exist at all? If you remember how self-attention works, every token has to look at every other token in that window. You double the text length and the attention work roughly quadruples. The computation simply runs out of room on the GPU memory. Think of it like a whiteboard in your office that has a fixed size. You can write whatever you want on it, but the moment you need to add a new paragraph, something old has to get wiped off. The board does not expand to fit your notes, it just stays exactly that wide. But here is the fact that surprises almost everyone. The model itself is completely stateless. It remembers absolutely nothing between calls. So, how do chat apps feel like they remember your conversation? They fake it by resending the entire conversation history with every single new message. Your prompt gets longer and longer because the app packs all those past turns right back into the input. And that is exactly where things break. Once that packed conversation crosses the context window limit, the system has to drop something. It always drops the oldest turns first. The model suddenly forgets what you agreed on 3 messages ago, because those early tokens just fell off the left edge of its view. This single limit is exactly why AI engineers have to build external memory systems and retrieval pipelines for their agents, which is precisely what we will construct later in this course. For now, you know how the window works and why it forgets. Next, let us look at why LLMs hallucinate, where those confident wrong answers actually come from, and why a confident answer and a correct answer are not the same thing. We just mapped how the model guesses the next word, but there is a quiet flaw in that guessing game. Our full pipeline layout holds every piece we have wired together so far. Right beside our output list, watch for this warning sign. Let us say the model knows nothing about your question. The ranked list of candidates sits completely flat, with 4 options hovering near 25% each. It still has to pick a winner, so it just invents something. Now look at case B, which breaks the common myth. Hallucination is not only a low confidence problem. Almost every junior engineer trusts that percentage bar until it confidently invents a library that does not exist. The model can put 91% on a completely fabricated book title or API method and be wildly wrong. Here is the real lesson. Confidence and correctness are two different things, and the model reports neither of them. In simple words, a high probability just means this token reads like our training data, not that it is a verified fact. The thing is, the model has no "I am unsure" output. So fluent nonsense looks absolutely identical to a real fact on screen. So where do these honest mistakes actually come from? You get gaps in the training data, out-of-date information, pressure from a leading question, and the plain fact that sounding right is exactly what it was optimized for. This is why you should care as an AI engineer. You cannot spot a hallucination by how confident our output list sounds or what that warning sign actually means. Our next 5 videos cover what you can actually do instead. Next, let us look at feeding an agent, where memory and tool results join the user question in one prompt. We just mapped how the model guesses the next word, but there is a quiet flaw in that guessing game. These are the real limits: no memory, fixed window, always guessing, and priced per token. Rule 1. The model is stateless, so memory is something you build and resend, not something it has. Rule 2. It cannot look anything up, so retrieval means putting the document text into the prompt yourself. Rule 3. It cannot act, so a tune call is just the model emitting text your Python code chooses to execute. Let us trace back to a pipeline layout where every component still follows those exact rules. There is no separate memory channel or document channel. Your code joins memory, retrieve documents, tool results, and your user text into one single prompt string before it is ever tokenized, which is why prompt assembly is real engineering work. This whole string goes into the context window. And watch what happens when you join them in. The token counter gauge pushes further towards its limit, while the price panel running cost jumps right along with it. The thing is, everything you add competes for the same window and the same attention budget. More context is not automatically better, because the model has to split its focus across all those extra words. You think you are feeding it a feast, but it is just trying to read a menu that keeps growing. Next, we will look at lever 1, where we turn the temperature down to stop the model guessing too wildly. We just saw how every piece of context feeds into one prompt, but the guessing game is still running. Let us map our first fix onto our pipeline layout. See, the model hallucinates when it has to guess, so every fix we add simply removes a reason to guess. Lever 1 is the cheapest of the 4. It is one number in your API call and costs you nothing extra. We tag it here as lever 1 because changing this single number changes how boldly the model picks its next word. Let us say the model is choosing from a flat spread. 4 candidates each sit near 25%. It has no strong support for any of them, so it reaches blindly into the tail. Now we turn the temperature down, and that flat list sharpens onto the few tokens the model actually has support for. The low temperature stops it reaching, so it picks from what it already knows. But here is the limit, because this part is usually skipped. When the model is confidently wrong, as in case B at 91%, a lower temperature makes it more likely to pick the fabrication, not less. So basically, temperature controls boldness, not truth. It only helps when the model was being reckless rather than mistaken. If it does not know the answer, cranking down the knob will not invent one for you. This is why an AI engineer needs to know exactly what this lever buys you. It is the first thing people reach for and the one they most often overtrust, so keep it in your toolkit but respect its limits. Next, let us look at how giving the model the actual document helps it read an answer instead of recalling one. We just turn the temperature down, but it cannot fix one stubborn case. The model sometimes gives you a confidently wrong answer, and lowering the dial does nothing to stop it. See, the move is nothing but a shift in focus. We take our source document and place it next to the prompt box. Instead of asking the model what it remembers from training, we just paste the text straight through. Let us say we ask a question about a specific contract clause. Before, the model invents a citation at 91% confidence. Once the genuine passage sits in the prompt, that fabricated line drops sharply and the correct token takes its place. Now let us drop this new move onto the full architecture we have been mapping. See, what you just built is exactly what we call retrieval augmented generation. The retrieval part only finds the right text to paste, while the augmentation is nothing but that text flowing into our prompt box. Watch how the retrieve documents node now carries a lever 2 marker, sending its actual content straight into the prompt. Now look at the token counter and the price panel beside it. In simple words, every word you paste is a real token, and you pay for each one on every single call. Why does an AI engineer care so much about this? Because the single biggest quality jump in most agents comes from this lever, not from switching to a bigger model. Next, we will let the model call your own code for a real answer instead of recalling one from training. Now that we have put source text into the prompt, let us look at facts that change after training finished. Lever 2 gave the model static documents to read. Lever 3 handles live data that shifts every hour. You already know the model only guesses tokens from its training patterns. But what about today's exchange rate or the current server status? The model has no live window to the outside world. See, a recall figure is frozen at training time, while a looked up figure stays current. If the model tries to guess a live number from memory, it will invent a plausible but wrong value. That is exactly why we let it call a tool instead of relying on its own recall. This is the part that trips people up most often. We start at the model output, then move to your Python code, and finally land back in the prompt input. The model cannot run anything on its own. A tool call is nothing but a short text request that travels to your code. Your Python layer runs the lookup, grabs the real answer, and sends it back into the prompt as ordinary text. We just traced how live data travels outside the model, so let us pin that round trip onto our architecture. Here is our complete pipeline layout so far. We simply tag the tool results box with lever 3 and draw a new connection beside it. The model emits a request out of the diagram to your Python code, and the real result flows back into the prompt. But here is where people trip. The model decides it wants a tool. Your code decides whether to actually run it. You keep full control over every external call. The model only suggests the request, and your Python layer validates it before executing. So live data always goes through a tool call. Next, let us look at lever 4. Let it say I do not know. We have wired up the tools and the documents, but there is one missing piece in that assembly. See, before the user question ever reaches the transformer, there is a quiet block of text sitting right beside it. We call this the system message, and it feeds directly into the prompt box alongside your question. The thing is, by default, there is no I am unsure output in that vocabulary list. So when the model has absolutely nothing useful to say, it still has to pick a word. It does not sit back and shrug like we would. It just guesses, which is exactly how hallucinations start. The fix is surprisingly simple. It involves the prompt box where all context meets. You drop one line of text into the system message, which travels with your user question. That single instruction then applies to every turn without you repeating it. So suppose we hit that same dead end again. Now when the model looks at its options, it sees a real choice. The flat spread shifts and I do not know climbs to the top of the list. The sampler picks it, and instead of an invention, you get an honest answer. Now, let us be completely honest about the ceiling here. All 4 of these levers reduce hallucination, but none of them remove it entirely. The model is still predicting patterns, not checking facts. So anything that actually matters still needs a human or a tool to verify it. This is why an AI engineer actually cares. 3 out of these 4 levers are just pieces of text you assemble into a single prompt. You are not tweaking math or training weights anymore. You are engineering the exact instructions that steer the model, which makes prompt assembly genuine engineering work. Next, let us look at the full picture start to finish, tracing one clean walkthrough from typed text all the way to a generated word. Now that we have plugged in our external tools, let us watch a single request travel through the whole pipeline. Every piece of context your application gathers sits waiting on the left. So the memory contents, retrieved documents, tool results, and system message all merge with your user question into one prompt. That prompt feeds straight into the tokenizer, which chops it into tokens. Those tokens become embedding columns, pick up a position number at the merge step, and flow right into our transformer blocks. If we pause inside any single block, the work splits into two clear jobs. Self-attention gathers context by letting every token look at every other token, and the feed-forward layer does the actual thinking on that gathered information. Once the signal leaves the stacked blocks, it hits the output list with a probability for every word in the vocabulary. The temperature slider decides how bold the pick should be. Top P trims the long tail, and the winning token loops straight back to the start. In simple words, an LLM predicts the next token extremely well over a limited window. As engineers, we work with three practical constants while this runs. Tokens cost money, the context window is finite, and the output is always a guess. It is quietly funny that we steer a trillion parameter system by turning two sliders and watching a counter tick up. You do not control the model weights, but you do control these four lever markers on the sampling panel. See, training, backpropagation, and GPU internals are model builder territory, not agent builder territory. We leave those where they belong. Your next step is prompt engineering, followed by your first real LLM API call in Python. Keep coding, and I will see you in the next one.